Welcome to the course on Basics of Computing. The objective of this module is to identify the character of a number, that is, we are going to check whether a number is Armstrong number or not. So as we stated in the algorithm introduction, first we must understand the problem very well. That means we must know what is actually an Armstrong number. Only then we can check whether the given number is Armstrong number or not. So the Armstrong number is the one with sum of cube of individual digits will give the number. The sum of cube of individual digits of the given number is equal to that number. One example for that is, if we take 153, then 1 cube plus 5 cube plus 3 cube supposed to give you again 153. So we are expecting the user to enter a number and we have to identify whether the given number is an Armstrong number or not. So we will see how to develop algorithms for this. So as we saw already about the problem, that is, it has to be 1 cube plus 5 cube plus 3 cube. That means we must be able to extract the digits separately. So the point is, first we have to extract each digit separately and you have to cube each digit separately, and finally you have to add it in one variable, and then you have to compare that variable with the actual input entered by the user. If both are same, then we will declare that as an Armstrong number, otherwise we will say it is not an Armstrong number. So this is how the algorithm must be developed for this. So first you will be giving the notation start. After that you have to read the number. The assumption here is the number user is not entering 0. If you want to check that case also, you can add the test case. And once the number is read, you have to initialize the sum as 0, because finally we will be adding all the digits cube value. So before any addition operation, we have seen already, you have to initialize the sum as 0. Then you will be processing with the actual number. So over the processing, your number will be changing. So the number will be divided by 10 every time. So the number has to be preserved. So you are storing the number in temp. So with the help of the variable temp only, we are going to process, so that the original number is retained in as it is. Then repeat step 5 and step 6 until the number is greater than 0. That is, until the temp, what is there in your temp? The user entered value. So until your temp is greater than 0, you will be repeating these two steps. The steps are: sum is equal to sum plus power of temp mod 10 comma 3. Temp mod 10 comma 3. That is, this is actually one built-in function in C. So if the algorithm developer is well known about the language, we can develop like this. Otherwise, I will give you another method how to write for this. Here the steps are, actually we have to extract each digit separately. So for extracting the digit, we are doing this operation, that is temp mod 10. When we do modulus operation, the last digit will be, the remainder will be the last digit that can be stored. So the last digit is now available for you from that number, and the power function is, if I am giving power of x comma y, means it represents x power y. So what will happen? The extracted last digit power 3. So we are cubing the last digit, and once it is cubed, we will be adding that with the sum. So these two operations are carried by this statement. First one is, we are extracting the digit with the help of temp mod 10, and once it is extracted, we are cubing it. The number power 3, and then you are adding it to the sum. Already sum is 0, so you extracted the first last digit, that is in the ones place. You have extracted and you have stored that value in your sum. Then what I supposed to do? I have to extract the second digit. So to extract the second digit, we are dividing the number by 10. So what happens? The quotient will be having only the first previous elements apart from the last digit. So once again you will go back and check whether the temp is greater than 0 and proceed this. This time your last digit is the last but one digit, that is in the tens place. So which again is supposed to be processed until your temp is greater than 0. Once we take one example and see this problem, we can understand it further better. When we come out of this looping process, we will be getting some value in the variable called sum, and you have to compare that sum and the original number. The sum and the original number. If both are equal, then you display the number is Armstrong number. If it is not equal, then it is not an Armstrong number. So the algorithm is extracting individual digits and cube power, every digit is cubed and then it is added in the variable sum, and the sum and the original number is compared. If they are not equal, it is not an Armstrong number, otherwise we can display it as an Armstrong number. So I told you already, if the programmer or if the developer is not well versed in the language, instead of this part we can use this. That is, our objective is to extract the last digit or one by digit. So to extract the last digit, we can have one variable, remainder is equal to temp mod 10, and then sum is equal to sum plus cubing means what? X into X into X. So X remainder into remainder into remainder. That will be added to your sum. So either this way or this way we can develop this algorithm. So to check this algorithm, we are going to have two cases. One will be the actual Armstrong number, the other one is not an Armstrong number. We will see how the algorithm reacts to both the inputs. The example one is, we have taken the value 371. Then as per the algorithm, we have initialized the sum as 0 and temp as 371, because when we process the temp, the original number will be retained as it is, so that at the end of the program I can check, I can compare sum and number. So what is the condition for us? Temp must be greater than 0. So user has entered 371 which is greater than 0. So we can enter into the loop. So once we enter into the loop, what is the procedure? Sum is equal to sum plus 0 plus, which is what the initialization for sum, 0 plus 371 mod 10. Temp mod 10. So 371 mod 10 whole power, that is what written as power of temp mod 10 comma 3. So this is what happening. So 371 mod 10 will give you 1 as the remainder. So 1 cube is actually 1. Then in the loop, next step is temp is equal to temp by 10. So 371 divided by 10 will give you 37. Then you have to go and check for the looping condition, whether temp is greater than 0. What is your new temp value? Which is 37. 37 is greater than 0, which gives you true as the result. So once it is giving true, then we are eligible to enter into the loop. Inside the loop, we have sum is equal to sum plus. So your previous sum is 1. So sum plus the new temp value, that is 37 mod 10, the whole power cube, that is equal to 1 plus, which is what your previous sum, 37 modulus 10 gives you 7. So 7 cube. So 7 cube is 343, which finally gives you 344 as the sum. 343 plus 1 will give you 344. Then we are in the loop still. The temp is equal to temp by 10. So 37 by 10 will give you 3 this time, and once again you have to go back and check. When you are coming to this step, you have to go for checking the looping condition. The looping condition is temp must be greater than 0. Yes, your new temp is 3, which is greater than 0, so which gives you true as the result. So sum is equal to previous sum, that is 344 plus temp mod 10, 3 modulus 10 power 3, that is whole power 3. So 344 plus 3 modulus 10, then it will return you 3. If only greater number is there, it can return you the remainder, or else it will return you the actual number. So 344 plus 3 cube is equal to 344 plus 27, which gives you 371 as your sum. Still, the system doesn't know that whether the process is over or not. So temp is equal to temp by 10. That is, new temp is 3, 3 by 10 is equal to 0. It will go back and check for this condition. Temp must be greater than 0, but this is not greater than 0. So the condition fails. Once you are coming out of the condition, you have to check whether sum is equal to number. So your sum is 371. And the number entered by the user is 371, both are equal. If both are equal, then you have to characterize the number as Armstrong number. With that, you can stop your code. Now we will see another example for the same problem. If the user is entering the number 421, it is not that only 3-digit number, any digit number which is capable by your data type what you have declared, you can give. There is no restriction for us. You can start from 1 and you can give any number according to the data type what you have allocated. Just for explaining simplicity, we have taken only 3-digit number. So if the user is entering 421, then as usual you will be initializing the sum as 0 and you are copying the number into temp, so that during the process it is going to be changing. So finally we have to check only with the original number. So the original number will still be retained in the variable called number. Then you have to check for the condition. The condition is whether temp is greater than 0. Your temp is 421, which is greater than 0. So the condition is true. Sum is equal to sum plus temp by 10 whole power 3. That is what this says. So 421 mod 10, which gives you 1, and 1 cube will give you 1. So now your sum is 1. The next step is temp equal to temp by 10. So 421 divided by 10 will give you the new value of temp as 42. Then again we will be checking whether 42 is greater than 0. Yes, it is greater. So we can once again enter into the loop. Inside the loop we have sum is equal to sum plus. So 1 is already calculated. So 1 plus 42 mod 10 will give you 2 power 3, which is actually 8. So 1 plus 8 is actually 9. Then temp is equal to temp by 10. So temp is equal to 42 divided by 10, which gives you 4, and this time also 4 is greater than 0. So which is true, we are eligible to enter into the loop one more time. So previously calculated value, which is 9, plus 4 mod 10. If the numerator is greater, then it will be returning only the same number. So 4 is returned. So 9 plus 4 cube will give you 9 plus 64 is 73. Then again you will divide your temp by 10. So 4 by 10 will give you 0. But this time the loop fails because temp must be greater than 0. So it cannot accept this. It will come out of the loop. So once you are coming out, you have to check whether sum is equal to the number. Your calculated sum is 73, but the user entered number is 421, which are not equal. When it is not equal, you have to display that as a not an Armstrong number. So this is the C implementation for Armstrong number, for checking whether a given number is an Armstrong number or not. So here we have declared the variable n for storing the number which is entered by the user, and we are going to store the individual digits cube in the variable. So for that we have sum, and we are actually storing the number in temp because over the process the number is going to be changing. So finally we need the original number. So all the processing is going to be carried over in the variable called temp. So our original number is retained in n. Finally we will compare our sum and n, and we will check if both are matching, means we will display that as an Armstrong number. So we have stored the number in the temp. While temp is greater than 0, until temp is greater than 0, what do we do here? Here we are extracting the digit of a number and we are giving the number power 3. With that operation, we are adding that to the sum, and for next iteration, the next digit has to be retrieved. For that, we are dividing the temp as temp by 10, and then you have to check this time whether temp is greater than 0. Until we reach 0, the operation will be performed. Every time we will retrieve the last digit and we will give the last digit power 3, and which will be added with the sum. So when we come out of this loop, we will be comparing the n which is entered by the user and the sum value, and they are equal. You have to display the given number as an Armstrong number. Otherwise, if they are not equal, you just display the number is not an Armstrong number. The next module is to check whether a given number is a strong number or not. So before proceeding to this algorithm, we must be knowing what is actually a strong number. So the characteristics of a strong number is sum of factorials of individual digits. Sum of factorials of individual digits of a given number must be equal to the number. Let us take an example as 40,585, then 4 factorial plus 0 factorial plus 5 factorial plus 8 factorial plus 5 factorial. That must be equal to 40,485 once again. That is 4 factorial is 24, 0 factorial is 1, and 5 factorial is 120, and 5 it will give you 8 factorial is 40,320, and once again there is a digit 5 which again gives you 120. If you add all together, you will get the original number back. So the numbers like this will be represented as strong number. So here the problem is user will be entering a number and we have to identify whether the given number is a strong number or not. So in this case we will be having two processes. One is you have to extract the digits separately and you have to calculate the factorial for each digit, and finally you will be adding all the values together and then you have to compare the sum and the original number. So this is a C implementation for checking whether a number is a strong number or not. So we know already strong numbers are sum of the factorials of individual digit which must be equal to that number. So we are having the variable for storing the number which is entered by the user, and as the number is going to be processed in this program, it will be supposed to be stored in the variable called temp, and then you finally everything supposed to be added. All the individual digits factorial must be added and compared with the original number. So for that addition process we have sum here, and once the value is read, you copy the original number to the temp until we reach 0, that is until the temp is greater than 0, extract the digits individually. So what happens when we give temp mod 10, the last digit will be extracted. So for that value we are calling the function fact. So fact is a separate function which will be receiving the last digits. Just for example, if I am having 1, 2, 3 as my input, temp mod 10 means it will give me 3. So fact of 3. So in this module we are finding fact of 3 and we are returning the fact, and that value is being added with the sum. Then you have to extract the next digit. For extracting the next digit, you have to divide the temp by 10. So once it is divided, you will be having only 12. That 12 is greater than 0. So once again we can enter. So this time 12 mod 10, which gives you 2. So fact of 2. So for finding the fact of 2, you are calling the function fact. So it will return you the factorial of 2, which will also be added with the sum. And once again 12 will be divided by 10. So what happens? We will get 1, and 1 is greater than 0, and the sum is equal to sum plus fact of 1 mod 10. That means which is giving you 1. So fact of 1. So each digit is extracted in this step, and for each digit we are calling the function fact, and this returns you the factorial, and the returned factorial is stored in the variable sum. And once you come out of this loop, the n and sum is being compared. If they are equal, you have to display that as a strong number. Otherwise, you display it as not a strong number. So we see several kind of number characterization and number identification. So one such character is a perfect number. To check for a perfect number, so we must be knowing what is actually a perfect number. Perfect number is a positive integer which is equal to the sum of its divisors, excluding the number itself. So we are going to develop the algorithm for finding a perfect number, whether a given number is perfect number or not. The category for that is, the character for a perfect number is, it is actually a positive integer which is equal to the sum of its divisor, excluding the number itself. Example, if you take the number as 28, the divisors of 28 includes 1, 2, 4, 7 and 14. We should not include 28. So we can include all the numbers other than itself, but the sum of all the divisors must give you 28 as the result. Then we can call the number as a perfect number. So here is the algorithm for finding or checking whether a given input is perfect number or not. So after reading the number, you have to initialize the sum as 0, because we will be adding all the divisors together and we will be comparing that sum with the original number. So for that we need to store the sum as 0, and I is initialized as 1 because the divisors are to be found from 1 to n minus 1, because we should not include that n value. Okay, so the steps to be repeated are 4 and 5. Repeat the steps until I less than number. So up to 4 to 6. So repeat the steps 4, 5 and 6 until your I is less than n. So the step 4 is, if number modulus I is initially 1. If number modulus I is 0, then add that with the sum. That is, sum is equal to sum plus I. And after adding it, you have to increment the I value by 1. Then you will be having I as 2. Then once again you will be entering into the loop after checking the condition whether I is less than the number or not. Then if that 2 is number mod 2 is 0, then also you will be adding. That means what we try to say, we will read a number from the user from 1 till the n minus 1. We will divide the number on each iteration if the modulus operation gives you 0 as the remainder, which is actually the divisor of the number which has to be added to the sum. That is what is being carried over with the steps 4 to 6. And once you are coming out of the loop, you will be having the sum in the variable sum which has to be compared with the original number. If both are same, then you declare that as a perfect number. If they are not equal, then it is not a perfect number. We will take two cases. One is actually a perfect number, the other one is not a perfect number. We will see how the algorithm reacts to both cases. So the first number what we have taken is 6. The user has entered 6. The sum is initialized as 0 and I is going to be started from 1. And the first condition is whether I is less than number or not. Yes, I is less than number, that is I is 1, the number is 6. So it is true. We have to enter into the loop. 6 mod 1 is equal to 0. 6 mod 1 is actually 0. So once it is true, we have to add 1 to the sum. So now your sum will be 1 and then you have to increment your I as plus 1. So I will become 2. Then again you have to check for the condition whether 2 is less than 6. Yes, it is less than 6. So we can enter once again. 6 mod 2 is also 0. So which has to be added. 2 is supposed to be added with the previous sum, which gives you 3 as the result. Then you have to increment your I as one step. So I is equal to I plus 1, which is giving you 3. 3 is also less than 6, which is also true. So 6 mod 3 this time, which is again to be added with the sum. So this I value is actually added every time. Whenever it gives you 0 as the remainder, you have to add that with the sum. Then your I is now 4. 4 is also less than 6. So once again you can enter into the loop. 6 mod 4 is not 0. Then what you have to do, you should not add this. You have to come to this step, that is simply increment your I value. And then I is less than number. 5 is less than 6. So it is true. So once you are entering into the loop, 6 mod 5, which gives you 0, which is actually false. It is not going to give you 0. So the condition fails. Then you are incrementing your I value, but I is not less than number. So the condition fails. When you come out of the loop, sum what you have calculated already is 6 and the original number is also 6. So both are equal. If both are equal, you have to display that as a perfect number. Here is the number will be read by the user and then you have to check for the condition whether the number I value is less than the number where provided I is started from for 1 and it is iterated till n minus 1. On each iteration you will be dividing the I value you are dividing the number by the I value and then you check whether it is giving you 0. If it is giving you 0, add that I value to the sum and finally check whether the sum gives you the number or not. If it gives you the same number, then it is a perfect number. Otherwise, it is not a perfect number. So the next case, we have taken the number as 5. Then you initialize sum as 0. I starts from 1. Then I 1 is less than 5, so we can enter into the loop. 5 mod 1 is 0, so which is true. So I have to add this I, that is 1 to my sum. So sum is now 1 and I must be incremented. Once again 2 is less than 5, which is also true. So 5 mod 2 is not going to give you 0. So for this condition you have to simply iterate the loop to the next state, that is I will become 3. So again 3 is less than 5, which gives you true, so that you can enter into the loop once again. 5 mod 3 is also not 0. So you will again simply increment your I value by one step, so that I will become 4 and 4 is also less than 5. So this last time you can enter into the loop. So 5 mod 4, which is also not 0, and when you increment this time to your I, which is actually 5, which is not less than the number which is actually equal to that number, so the condition fails. Once you are coming out, you will be having only 1 in your sum, but the actual entered input is 5. Both are not matching, so that we can come to the conclusion that it is not a perfect number. So this is how the algorithm handles perfect number as well as not a perfect number. So this is the sample implementation for finding whether a number is a perfect number or not. So to check whether a number is a perfect number or not, you have to add all its divisor other than its own, and you will be storing it in a value called sum, and finally you will be comparing the sum and the original number. If both are equal, it is a perfect number. Otherwise, it is not a perfect number. So as usual, you are declaring variables for holding your n and for holding the sum and for iterating, for finding the divisors of the number. So the number is read from the user, and from 0, actually it is required from 1, it is not required to 0. So I is supposed to be from 1, from 1 till less than n, because that n is not to be included. Though I say 12 is a factor of 12, I should not include 12 for calculation of perfect number. I should calculate only up to less than 12. That is why I must be less than n. Then for every iteration you increment your I value and check whether the next number is a factor or not. Then if n mod I is 0, that means it is a factor. So you add the factor with the sum. I is to be added. How long you have to add? Until you reach n. So once you come out of the loop, you will be having the sum of divisors in the variable sum, and then you compare sum and n. If both are equal, you display it as a perfect number. Otherwise, it is not a perfect number. This is how a simple implementation of perfect number can be written in C language.